Chapter 7. And this one is a bit longer than Chapter 6, so we are going to be here for about 3-ish weeks. Our test for this Chapter 7 unit is like on Thursday, May 5th. So we have a little ways to go. And today we're going to be thinking about exponential growth. And so our learning targets are first going to be writing an exponential equation that matches a real-life situation. We're also going to determine if a relationship describes linear or exponential. And finally, we're going to understand the relationship between growth factor and percent increase. Our homework for tonight is the colored sheet of paper I had you grab here on your way in. So I'm calling this the 7.1 Part 1 assignment. And something that we're going to try, this is going to be a little bit different here for Chapter 7, to try to save some more of our in-class minutes that we have together. I will post the solutions for this assignment on Schoology for you. So we will have a few minutes at the start of class Monday to touch base, like if you have questions on any of the answers you saw. I absolutely want and need you to try the problems first on your phone. The solutions, it's just like that step that we do in class where we check our answers at the beginning to get some feedback and see how you did, and then we'll probably just collect it into our folders. So that will help us in getting through the great things we have planned here for Chapter 7. So today is all about Fred and Andy. So these are two friends, and on the same day, they each buy a colt, like a little baby horse. And both colts have a starting weight of 50 kilograms. 1 month goes by, and the friends come back together, and they compare the weights. So Fred says, my colt grew 10 kilograms. Andy says that his grew 20%. Another month goes by, and they meet again to compare their weights, and Fred says, mine grew another 10 kilograms. Andy says, mine grew another 20%. So we're going to start by determining the weight of the colts 2 months after they were bought. All right, so I'm going to put Fred on this side. We've got Andy over here. Ariana, would you tell us, what did you get for the two weights, and how did you get there?
For the first one, for Fred, you add 10 for both months. And then for the second one, you just find 20% of 50, which is 60, and then you find 20% of 50, which is 70.
Okay, so thinking about what we're adding on in the first month, so 20%, hold on, 20% of the starting weight of 50 is going to add on 10 kilograms. So then at the end of the first month, now Andy's is at 60 kilograms. But then it's going to grow 20% again. So when we take 20% of the 60 kilograms, we see that we're adding more than we added in the first month. So now from month 1 to month 2, we're actually adding 12 kilograms instead of 10. And so that's going to get Andy's to an ending weight of 72. So what we're going to do next is think about this pattern continuing itself in the same way for a few months. We're actually going to go all the way through to the end of the 8th month. And so let's go ahead and fill in what we've already seen so far after the 2nd month. So we have Fred at an ending weight of 70. And the process that we're doing over here for Andy, so we're always taking the previous month amount, that's what's in first, and then notice how we're adding on 20% of the previous amount. So that ended up giving us this answer here, 72. So what was interesting that I think surprised some of us is that the amount added was not the same every time. So in the first little piece there, that 20% times 50 resulted in adding 10 kilograms. But now when we do 20% of 60, this results in adding 12 kilograms. So I would like you to continue this process and fill in the rest of the values in the table. All right, so as we start to take a look at the ending weights here in our table, it's kind of interesting to see that early on, Fred and Andy's colts were at pretty similar weights at the start, but we see it break away as we go further in months. We see the differences getting greater and greater. I mean, at the end of the 8th month, Andy quite different between the two. So what we're going to do now is take these values from our table and we're going to transfer them over to a graph. So we have a grid on the right-hand side of your page. You can see that we have months on the x-axis, we've got the weight on the y-axis. We're actually going to graph two lines, one for Fred, we'll do that in a dotted line. We'll do Andy's in a solid line, and we're going to see how it looks graphically. Now, they actually both have the same position to start with because at 0 months, they both have a starting weight of 50. It looks like that's the y-intercept here on our graph. And actually, after the first month, they both have a weight of 60. And then this is where they're going to start to branch off. So on Fred's, after 2 months, he was at 70. Andy's was a little bit higher at 72. Then after 3 months, we see that Fred's is 80, and Andy is all the way up at 86.4. So notice how that distance between the 2 points, that vertical gap, seems to be increasing. And as we continue with the months, that gap is only going to get greater and greater. So looking at the 4th month, it looks that Fred's is now at 90. And after the 4th month, Andy's was already at 103.7. Okay, look, that gap is getting bigger. So let's go ahead and continue to fill in the rest of the points. We'll do this all the way up to month 8. Fred's is a little bit easier to fill in, because every month we're just adding 10 kilograms. All right, and once you have your graph done, I want you to take a moment to answer questions A and B. So you're going to answer what seems to be the most striking difference between the two graphs. And part B is, do you think either of these growth patterns is realistic for a longer period of time? All right, everyone, so let's come back together here. So the difference between the two graphs. Leah, would you share out what you wrote here for part A? Okay, which is which? All right, so we're going to put in a few labels here for the type of line, the type of graph that we're noticing, and some characteristics here on the graph. So notice how Fred's, being linear, this one's straight line. And it makes sense because it was increasing at a constant rate. Every month, add 10 kilograms. Another month goes by, we add 10 kilograms again. It's like the slope of that stair step is the same all the way through. In fact, the slope is 10. That's what we're adding each time the number of months increases. Notice that for Andy's up here, this one had a little bit more of a curve to it. And so although it looks somewhat straight near the start, because the vertical distance, because the vertical gaps from one point to the next are just continuing to get bigger and bigger, it's not perfectly straight. It's going to have a little bit of a curve to it, and that's characteristic of something that's exponential. We also see that the exponential side was getting really big, really fast. And so when we have a growth process, like when the line starts to get really, really steep, we use the phrase, it's growing exponentially. It's exponential growth. Okay, so we're going to take, oh, I'm sorry, I almost forgot about part B. Do you guys think that these growth patterns are realistic for a long period of time? No. At some point, these horses, I mean, it's not going to be like a 1 million kilogram monster horse, right? That would be quite scary. At some point, that growth is going to slow down and probably stop altogether. And so what's helpful to think about is anytime we're trying to use a mathematical model to describe something in the real world, there's going to be a point where the model breaks down. And so we might be able to model the growth like this at the very start, but imagine that these are both going to flatten out. So then, most likely for the remainder of the horse's life, it's just going to look like a flat line. This is just showing what's happening at the beginning. And it's like this for, like, if you have kids, they have these growth charts that kind of look similar to this. Like, there's these different curves, like you go to your pediatrician checkup and they see where your kid's height and weight is and where they are on the growth chart, and eventually it flattens out. Okay, so we're going to take one last look at the values here in the table for Andy's colt. And our goal, so one of our learning objectives for today was to write an exponential equation that matches a real-world situation. So our goal is to see if we can write an equation that's going to output the weight of Andy's colt when you input a certain time in months. Okay, so we're actually just looking at the values we got here for the first 5 months. These are just directly off the table that we did on the other side. And I want us to think down here about the relationship between two subsequent months. So specifically, we are going to do the weight this month divided by the weight last month. And we're going to look at this for a few different pairs of weights in our table. So we're going to start by looking at 50 and 60. So we're going to start with 60. So think about the weight this month at the end of month 1. That's going to divide by 50, which would be the weight last month. All right, and notice how this result ends up being 1.2. Now, if we were to go the other direction, that also means that 50 times 1.2 should give us the answer of 60. Let's do this for another set of values in the table. So if we look at the difference from month 1 going up to month 2, the ending weight at the end of month 2 was 72. We're going to divide that by the ending weight at the end of month 1. Notice how we get 1.2 again. So 60 times 1.2 should be 72. If we check it for one more, the weight at the end of the 3rd month divided by the weight at the end of the 2nd month, that was a little crazy, we get 1.2 again. So if we were to continue checking all the values, we should see that every time the ratio ends up being 1.2. So what that's actually showing us here is there may have been a faster way from the very beginning to figure out the weight for Andy's colt. Every time we go forward 1 month in time, we're actually just multiplying the values by 1.2. So let's think about this value that we have here at the bottom of our table. So at the end of the 6th month, we see that the weight is 124.42 kilograms. Well, what's really happened with the numbers to get up to that point is we had a starting weight of 50, and we multiplied by 1.2, and then we multiplied by 1.2 again. We multiplied by 1.2 a total of 1, 2, 3, 4, 5, and when we did that 5 times, we got 124.42. So off to the side here, we could have actually written this a different way. So let's think about starting with 50. And here I'm just going to show if we multiply by 1.2 5 times, we get 124.42. You can check that on your calculator. That should equal that weight. Now here's my question for you, because that's kind of a long thing to write out. Is there any shorter way or another notation that we could have used there? What can we do, Akira?
1.2 the third.
Yeah, and in this particular case, how many 1.2s did we have? Yeah, so we can just replace, or we can just utilize an times something is being multiplied by itself, and that's going to be a lot shorter than writing out this whole long thing. So at the very end here, we can say, all right, well, this is really just 50 times 1.2 to the power of 5. Now, there's actually one other adjustment we're going to make here. I actually don't love using the x symbol for multiplication because I think it could get confusing. We don't want to confuse it with a variable x. And so instead of that, we still are representing that we're multiplying, but I would instead like you to put your 1.2 in parentheses. We're still going to put the 5 exponent on the outside, but this is just going to be a different way of representing the same thing. Final thing I want you to notice here is notice that the value of the exponent, which was the number of times we multiplied by 1.2, that was the same as the number of months. So it turns out that if we wanted to do this for any number of months, if we know the number of months, we could just put that here in the position of an exponent, type one simple thing into our calculator, and figure out what the weight would be. Okay, so up here in this space, we're going to write a general equation now. So we want it to output the weight. So I am going to use a W to represent the weight of Andy's Colt. And every time it's going to begin with that 50, because that was our starting weight, that's our starting value. And that 50 is going to multiply by 1.2, a certain number of times. We're going to have 1.2 in parentheses raised up to the power of t. So instead of putting a 5 in there for the 5th month, t is just going to generally represent whatever number of months we're interested in. So we're going to actually put some labels here into each of these positions. So t is the number of months. I'm going to go back up here to the very start. This is going to be the weight after t months. And the 50 here, this was the starting weight. I'm going to actually write this as the starting value. And that's when t was equal to 0. So in other words, when it had been 0 months, the starting weight of the colt was 50. And then we're going to give a name to the 1.2. So the meaning of the 1.2, we know it's the value that the weight is multiplied by every month. The name we're going to give that is called the growth factor. All right, now before we turn over to the back, there's two more quick things that we're going to go and label back on the first table that we made. And it has to do with that difference between an exponential pattern like this one and a linear pattern like the growth of Fred's colt. Now we saw the difference between linear and exponential on our graph. Let's take a look at what that difference would be in a table of values. So starting on Andy's side, what we just found out there with coming up with our equation is that we're really just multiplying by 1.2 to get the next weight. We know that Andy's is an example of exponential growth, so let's put the exponential label down below that side. And a characteristic of an exponential pattern is that it's going to continually multiply by the same number. In this case, it's going to multiply by the same number every month. All right, now that is a little different from what's happening over here with Fred. So we saw Fred was just adding the same number every month. And that is a characteristic of linear growth. So if it's linear, we're going to continually add the same number here to connect it back with our story, but really the month is like the x value. And so if every time the x value gets bigger by 1, are the y values adding the same number? Well, then it's linear. Or if the y values are multiplying by the same number, then it's exponential. Okay, when you're ready now, let's go ahead and turn over to the back. All right. So we had 3 learning targets today, and we have kind of a different shaped box here. I'm still going to think about dividing it into thirds, but I'm going to do it 3 big sections, like horizontally. So the first one here was just to write an exponential equation to match a real-world situation. So I'm just going to call this first part here exponential equation. All right, so the general form for this, so instead of using W to represent weight, I'm going to make it a little bit more general. I'm just going to call the output Y. And we're going to write this as A multiplied by B in parentheses there, and that B is going to be a number that is a base that is holding up an exponent. The input of an exponential equation is in the exponent position. Notice that's where the x is. That's where the name exponential comes from. So the A out in the very front is going to represent a number. This is going to be the initial value when x is equal to 0. For us in our problem today, it was 50 kilograms, because that was the starting weight of the colt when time was equal to 0 months. Now we know whatever number goes in the position of B, literally that is the number that the y values are going to multiply by each time. The name that we gave it is the growth factor. All right, our second learning target had to do with the difference between linear and exponential. All right, so just a general description here is that every time x increases by 1, a linear pattern means we're going to see the y values add the same number. And actually that number that is adding every time, that's the slope of the linear equation. If it's exponential, the y values multiply by the same number. And the number that it multiplies by each time, that's what we call the growth factor. All right, now our third learning target had to do with understanding the relationship between growth factor and percent increase. All right, so to help us generalize this relationship, we're going to think about the specific values that we used in our problem today for Andy's colt. So the Andy colt story had a growth factor of 1.2. And then I want you to leave a little bit of space there. And then over here on the side, that corresponded with a percent increase of 20%. So we're going to describe the relationship here going in both directions. How do we get from one to the other? So let's say we know the growth factor, and we want to figure out what is the corresponding percent increase. So we're going to think about mathematically what exactly is happening with a 1.2. There's two things that are happening. So the first step would be subtracting 1. So if we have 1.2 and we subtract 1, we're left with 0.2. If we want to turn 0.2 into 20%, if we want to turn that into 20, we have to then multiply that by 100. So when you multiply by 100, it's going to move this decimal 2 spaces to the right, and that's how we get the 20%. Another way you can think about this, going in this direction, is ignore the 1 in front, look at the 0.2, and then just turn 0.2 into a percent. It's just, what is the little percent part that's added on to the end? What is the extra that's causing it to grow? Now, let's say we wanted to go the other direction. So we have the percent increase, and let's say that we want to turn it back into a growth factor. Well, starting with the 20, if we do the first step of dividing by 100, that's going to turn it into 0.2. And then once we have 0.2, we just need to add 1 to turn it into 1.2. And here's why it's valuable to know how to go back and forth between them, is because growth factors are what we use for equations. So notice how the equation that we wrote out for Andy's colt, it had 1.2 in the equation. Like that was the base that was holding up the exponent. The reason that we care about the percent increase is because this is what we use for stories. So if I want to tell a story, like what is happening with this equation, I'm not going to say that Andy's colt grew 1.2 every month. That could be confusing. Instead, I'm going to say that Andy's colt grew 20% every month. So in number 1, we're just given a new function where we want to start by identifying the different pieces, and then we're going to see if we can turn this into a new story. So just by the position of the numbers here, we can see that the starting value is 5. Growth factor would be 1.13. Well, when we turn that into a percent increase, it's actually just something grows at 13%. You have a lot of freedom in the stories that you write. So for mine, I was thinking about puppies today. So we need to have something that starts at 5. So my puppy has a starting weight of 5 ounces, and he gains 13% weight every month. Yours doesn't have to happen every month. It could be every day. It could be every week. It could be every year. In your story, you decide what that time period is going to represent. In number 2, we can think about doing that division. So take the ending amount, dividing by the previous amount to see what is that common ratio. In this case, when we divide, they're all equal to 5. And so that means here in our table, we multiply by 5 going forward. So that means that we're dividing by 5 if we go backwards. And so that's going to help us find the missing values for J and K. When we turn it into an equation, the starting value is 3. It's whenever x is equal to 0. Y value is 3. And then because we're multiplying by 5 when we go forward, the base holding up the exponent, the growth factor in this case is 5. Make sure that you write x up in the position of an exponent. It's not being multiplied by the 5. That would be something that's linear. Your x needs to be an exponent. And And then finally here, looking at the tables, we're just looking to see, we have a table and then we have a story. So anything with percent growth is going to be exponential, kind of like Andy's quote. In your table, if it's adding the same value each time, it's linear. And when you multiply by the same value each time, you could multiply by a fraction.